Good morning, everyone. So tomorrow is quiz, right? Just to make sure. I already prepared the question. Maybe today I will review one or two questions and then get into bit the double integral. Okay. And then I think we can finish the class in 1 hour. So maybe two questions from here. Maybe from the first one about the directional derivative and about the local minimum value. Okay. So maybe which number you prefer? From 45 to 47, which one? I think one question is on the question last week, right? I forgot which one. How about 46 or 47? Which one do you think maybe we can do? 6, okay, 6. So we have a function x, y, z. Okay, this is the function, and we have the point 1, 2, 3, and then we have the vector. The vector is 2i plus k minus 2k. So it's asking the direction of derivative. So let me write just a general expression for directional derivative, which is d. Usually this is v because it's a vector v, right? So dv will be of f at 1, 2, 3 is equal to the del of f at 1, 2, 3, and its dot product to the unit vector. Remember that this v need to be a unit vector, okay? So first maybe we could take the v and we define the unit vector as a vector v divided by the magnitude value of that vector, okay? So this will be, the magnitude is 1 over square root 4 plus 1 plus 4, right? This is, or maybe write 2 squared plus 1 squared plus negative 2 squared, okay? And then the factor, or maybe let me write the factor on here. So vector is 2i, or maybe in this term, maybe, okay? So 2, 1, negative 2. So this will be, it's become 9, so square root will be 1 over 3, 2, 1 and negative 2. Okay, that's the unit vector v, okay? And then the next one is to find the del, which means that this is going to be partial x, partial y, and partial z, okay? So del f, we start by taking partial x. We can write one by one if you want, like to make it clear, it's okay. So we can write this will be 2xy plus square root of 1 plus z, right? And then partial y, we have x squared, and there's no y on the second component, so we could just leave that as a constant, so it's 0. And partial z, we only have in the square root, so we have so we need to multiply with x and then divide by 2 square root of 1 plus z, okay? So we have everything, and we need to evaluate at 1, 2, 3. So evaluate, so add 1, 2, 3, partial x become 4 plus 2, 6, right? And then partial, or maybe partial y is 1, partial z is 1, and then 4, 3 plus 1 is 4, 4 square root 2, so 1 over 4, right? So del f. So del of f at 1, 2, 3 is 6, 1, 1 over 4. Okay. And we write again the dvf, the directional derivative at 1, 2, 3 becomes 6, 1, 1 over 4. I think we can multiply inside, so become 2 over 3, 1 over 3, and negative 2 over 3. And then multiply and then plus. So 6, so 12 divided by 3 is 4, plus 1 over 3, plus or minus negative 2 over 12, so negative 1 over 6, right? So what will be? 4, 12, so 13 over 3, so become 26 over 6 minus 1 over 6. So it becomes 25 over 6. Okay. So basically, whenever you calculate the rational derivative, if you have the factor, don't forget to change first to unit vector. Okay. Unit vector, like that, the green symbol. And then remember the idea, the rational derivative is the gradient factor or del, this inverted triangle, del, multiply with the unit vector. Okay? We use the dot product. Okay, so this is dot product. So this will be dot product. Okay. So the expected answer for the value for the rational derivative is a constant, usually a constant, not a vector. It is scalar. Scalar.
So I'm sorry. After we multiply like the I, J, K values of each other, we can just add it together for the final answer.
Yeah, this is the dot product. So which means that this plus this plus this. Okay. Dot product. So factor multiply with another factor using dot product will result as scalar, right? Scalar value. And remember that whenever we have this bracket, this is a vector. So you can write this is like 6i plus 1j plus 1 over 4k. You can write like that also. Okay, that's the number 47. Now from 51 to 54, any suggestion which one should we take? We need to find like maximum value, minimum value, and saddle point if they have a saddle point.
We have to graph.
It's your encourage, but not really.
I mean, like for tomorrow.
No. This is just like encourage is to see the real graph, like maybe using some like GeoGebra to see whether our answer is correct. This is just a for practice one. So do you feel which one? 3, 2, 1, 4?
Maybe 4.
4, okay. Take this one. So basically, what is the idea for the maximum minimum value? So maximum minimum value, we can start by, so let me write again the function here. So 54. So the idea is, the first thing what we can do is we can take the partial x and partial y. Okay, we can always try the first steps as finding the partial. So partial x, we only have x squared inside here, so it's just 2x, and then the other one will be e. So this will be 2x and then e y over 2, right? And then partial y, partial y, we have a product rule. So this will be 0 and 1, and then so e plus half e, and then half e, and multiply with this. So if I write like this, okay, I think we can take that. So plus 1 plus half x squared plus half y. We can also write, maybe to make it more clear, I will remove all the 1/2, so this will be 2 plus x squared plus y, and this will be divided all with 2. Okay, or maybe to make it simple, I think I can write half in the front. So we have partial x, partial y, and then okay, let me, maybe too much equation here. Let me resize. And then we can take the partial xx, just to make sure that we have correct. So 2e y over 2, and partial xy is half 2xe, or this is xe y over 2. So first we could take the the partial x to be 0. Remember that in calculus 1 we find the critical points. This is the same thing, we need to find critical points. So when partial x 0, if we look at the components, the only way that this x or the whole thing can become 0 is by making the x equal 0, right? Because the e is always positive. So we can conclude that this x should be 0. And then we can also try the partial y equals 0 to find another critical points. And we see that half e 2 plus x squared plus y equals 0. And then we could see that from this structure, okay, we can focus on this part, right? So 2 plus x squared plus y equals 0. And then we can substitute the x equals 0 here. Okay? So it means that this is going to be 2 plus y equals 0, and y is -2. So we could have this point xy, so critical is 0, -2. Okay, and then we could try this point. Okay, I don't think we could have more points, right? So we could start from this point here, and then we could check and finding which one is maximum, minimum, or saddle. So how do we check? We could write that D is fxx right? Or no? Squared, right? Okay. Oh, I forgot to write the yy. Let me write here yy. The partial yy is half e y over 2 plus 1 over 4 e y over 2 x squared, and then it's too long. Let me write, maybe give space here and space there, resize a little bit, and also resize this one. So fyy is 1 over 4 e y over 2, and then we write all this, and then plus plus 1, and then adding this one, right? Using the product rule, and then simplified. This will be e y over 2, so 2 over 4, half, so 1. So I think because all will be over 4, I will write 4 plus x squared plus y, and then adding 1 over 4 in the front. Maybe to make sure, right? Okay. So we check the point. So check the at 0, -2. So partial xx, checking the 0, -2 will be 2 over e, right? 2 over e. And then partial yy, so -2 and 0, so this will be 4, -2 is 2. Let me write here 2. -2 is -1, so 1 over 4e, so 2 over 4e. So we could write here, multiply with 1 over 2e, so 1 over e squared, right? And then minus fxy, it will be 0. So this will be e with power of -2, which means that this is a positive number, right? So this is going to be greater 0. And then we check the partial xx at the 0, -2, which means that this is going to be 2 over e, right? This is 2 over e, which means also this is a positive. So both are positive. For d is positive, the partial x is positive. So the point 0, -2 is a local minimum value. Okay, remember, if you have d, but if this is less or negative, it will be saddle point directly. Okay, but if we have d positive and checking the partial xx, if partial xx is less, it will be local maximum. But if this is positive, it will be minimum value. Okay. So so d. So every time you check d first. If this is positive, there are two possibilities. Can be maximum, can be minimum. If this is less, it will be saddle point directly. Okay? So if this is positive, we need to check the partial xx. Partial xx, check if positive is minimum. If negative, it's maximum. Okay. So let me write here, maybe to help you. So D can be positive or negative. Okay. If negative, this will be saddle. Right. Now, if positive, check the partial XX. If this is positive, this will be minimum. If this is negative, this will be maximum. Okay. Please keep in mind, you will get at least one question for this. So remember the steps, the procedure. First is finding the critical points. How to find the critical point? From the partial x and partial y equal to 0. And then solve the system of equations. You can substitute, basically you can try some method in linear equations. Like substitute this x from here on, you can get to this point. And sometimes maybe more than 1 point, maybe 2 points or maybe 3 points. It depends on the case. For this case, it's exactly 1 point that we need to find and determine. But sometimes there will be more than 1 point. It can be 2, 3, 4. Okay. Or sometimes if it is quite extreme, like having the order of the degree can be like 4, 5, 6. So maybe it can be like 6 points, 7, 8. But sometimes the number is repeated, like it has like combinations, like 1, -1, -1, -1, 1, 1, and then maybe -1, 1. It can be combination like that. And you need to check all the point, checking through this, and careful on the negative signs, okay? Sometimes it will be different. Like if you are, maybe the D can be written also, D can be written as, D is from the determinant in matrix. So you can write like this. So multiply and then subtract with this square. X, Y, and Y axis are the same. So we can just write as X, Y, and square. Or Y axis is also okay. Square. The same. Actually, you can try YY, similar with the partial XX for trying the positive. But I think I will give you the default by partial XX, which will help you just stick with this one. Okay. Hopefully you can try more exercise. Okay. Okay, the next part, I will continue, okay, so for the multiple integrals, because I don't think we have much time finishing all the contents, so I think we should move, right? So last time we finished the double integral, actually, we finished. And now the next section is about the polar. Okay, so let me open the new part, okay. So it is the double integral in polar coordinates. So basically, they are similar. Okay. The difference is we are going to exchange all the Cartesian into polar. So remember that when we change the Cartesian into polar, when we convert, there are at least 3 equations that need to be remembered. That is the circle equation, and then the trigonometric conversion for the x, y to r theta, using all these 3 stuffs. So we are going to exchange all the x, y components into the r and theta. So whenever we have, like, for example, this case here, so we have a circle in Cartesian, which is x squared plus 1, x squared plus y squared equal 1, like this. We can think this like from this axis, we create a circle by taking the theta from 0, full circle, and then back here, which is 2 pi, right? So we can say that the theta went from 0 to 2 pi, full circle, and then the radius is always constant radius 1. So we can say we can write in r theta as 0 less than r less than 1, and 0 less than theta less than 2 pi. Okay? And how about if we have like two circles like this? And then we would like to state this green region. Similar from this first circle, but we have now two radius. The radius is 2, and this second one is 1. So we could think that the radius is changing from radius 1 and then goes to radius 2. Is x squared plus y squared equal 4. So 1 less r less than 2. And then since this is only semicircle, not the full circle, so we could think that from 0 and then went through here and then stopped at pi. So 0 less than theta less than pi. Okay, I think it should be okay from that. And now our next goal is to define how, if we are going to evaluate the area in terms of the polar coordinates, in how the double integral works. So basically the same with what we have before, where we change everything into r theta. So I think let me just write a quick graph. So let's say we have a surface as usual, like maybe this is a surface. But now when we take down here, we would have, and we try to make this like with some sort of shape that can be traced using the polar. Okay? So now the area here, the region, can be traced in polar system. And the surface here also can be written as a function of r theta. So this is now our goal. So sometimes perhaps the information that was given is xy, but when you change to polar, maybe it will become easier to solve. Okay? And then first we need to define the area first. Okay? How to make this into our double integral. Okay? Because in double integral, the important thing is to define the dA. Right? If you remember, dx dy, dy dx, right? So we need to define the dy dx and dx dy in terms of r and theta. Okay? Now we can see here. Let me just zoom out a little bit. So we have this like a pizza, right? Like a pizza. And based on the pizza that we defined here, we could write the theta as changed from this part and then to this part. And we can say theta is from alpha to beta, and also we have different r from A to B. Okay? And then similarly with what we approach, we cut them and then we slice, and then we see that the small rectangle here. Okay, and the small rectangle here, we can pinpoint the coordinates as r theta, or we say ri as a sample point and theta j as a sample point. Okay, and all the terms we can write ri minus 1, which means the previous one, and also the theta j minus 1 and theta j. So we could see that the change in theta will be the delta theta. So we can write here first that the r, or the region r, we can define based on r theta. So a less equal r less equal b, and then alpha less equal theta less equal beta. And from the center of this polar of this rectangle, we can write rij ri minus 1 less than r less than ri, and then theta j minus 1 less than theta less than theta j. Okay. And then let the sample points of the ri sample points is half, or the average, okay, average of these two, and then theta j also the average. And then we are going to evaluate the delta A, which means the rectangle. Okay? There is the small rectangle. We would like to approach the, so if you have a circle, if you would like to compute this area here, if we have a theta, and we want to know the area, if this is with the radius r, the area is equal half r squared theta, right? If you remember, this is coming from theta over, the full circle is 2 pi, multiplied with the area of circle. What is area of circle? Pi r squared. So after cancelling, we get that this will be this, right? It's the same or similar with the first chapter we tackled, the chapter 10 about polar coordinates, right? So delta A, we could write that as the difference between half ri squared delta theta minus half ri minus 1 squared delta theta, or half ri squared minus and then since we can use the definition from the previous one, and we could write and factorize both of this, we can write as ri plus ri minus 1, and this would be ri minus ri minus 1, right? And then multiply delta theta. Now this will be ri, right? And this will be, let's say, the delta r, okay? So we could write this delta A, let's say AI, okay, to make it clear that this is the small rectangle. So we can write this as ri delta r delta theta, okay? And because of that, we could define the Riemann typical sum. So Riemann sum sum will be sigma sigma. The first is for I to m, and the second is j to n of the function Ri sample point cos theta j, and then y become Ri sine theta j, and then delta ai. This equal we can write f Ri cosine theta j, Ri sine theta j, and delta A becomes Ri sample points delta R delta theta. Now, of course, from the Riemann sum, we could rewrite the double integral. Okay, we could write the sum, the sigma notation as an integral. Or maybe if you write more specifically, more simple, we could also do that. And we can just write in terms of g, and this is in terms of r and theta. Delta r, delta theta. If g is a function of the r and theta. In short, in summary, the double integral, what we need to think is, we need to know first is r as our endpoint, and the second is the theta. And it should be written as double integral, and always this is r, and the inside will be the theta. Sometimes you can switch if this is a constant. Like the Fubini theorem, we can use that as well. But if it's not a constant, then we need to try find a way to compute the double integrals. And the form, if you see this f here, the n form is always r, and this will be delta r, delta theta, or r, dr, d theta. And so don't forget the additional r at the end of the integration. So if you remember the previous one, it was dx dy, dy dx. And now it's not only dr, d theta, but we need to add some r before the RD. Okay.
Professor,
Yes?
in the Riemann sum, is that delta AI?
Yes, AI. It means the small rectangle. Okay, and then as a conclusion from the definition, we could write that maybe before this. Maybe let me write something first here. That this r f x y dA can be written as limit, and this is double integral of F Ri sample point cos theta j, and then Ri sine theta j, which means that xy convert to the polar, and then delta ai limit as we add and cut the rectangle more and more, larger and larger, closer to infinity. And we can substitute to the g, which is function of r theta. And this is delta r delta theta. This is equal to alpha beta a b g r theta d r d theta. Or in terms of f, this will be alpha beta a b f r cos theta r sine theta, and r dr d theta. Or we could see these operations as double integral f x y dA. We can convert xy through r cosine theta, r sine theta, and the dA becomes r dr theta. The picture below is, I think, oversimplifications, how to intuitively see that if we have, so this part here, the arc of the circle, if you remember, this is equal to r theta, right? So when the angle is small, we could write this as r d theta. And if we try to take the concept like very, very small subset of this one, we could see that we can simplify this as a rectangle, which means the area will be dr multiplied with r d theta, which is r dr d theta. Just to oversimplify how to like get into the logic very quick. How to get the one is there's a big r here. The r is actually coming from the sector, okay, the r d theta. So this one here, so dA is r dr d theta. And you need to write precisely r dr d theta. Okay, the default, you need to write this first. Later, if in the computations we can see that this is constant, I think as long as we can know how the inside equation, if we can separate r and theta, we can separate also the integrations, or even we can switch the integrals. Okay. But I think for most of the case, apolar, later we are maybe unable to do that for some cases. Okay, I think I will just stop until here. Okay. Any question first? So don't forget to practice for tomorrow's quiz. So don't forget, tomorrow is quiz. I prepared 4 questions, and I think should be okay. If you can do the previous question, like for the first 2 questions I tried today, if you can do it by yourself, it should be okay. You can use calculator if you want, but I don't think the calculation is too complicated. Okay, I think it should be okay if you focus on the concept. Okay. At least 1 question about maximum minimum value. Okay, remember of that. Okay, so that will be the